Quantum mechanics embraced probability and uncertainty, challenging Einstein's deterministic worldview, EPR Paradox and Bell's Theorem. Imagine you have a magical pair of gloves. One is sent to New York and the other to Tokyo. If you look at the glove in New York and see that it's a right glove, you instantly know the one in Tokyo is a left glove, no matter how far apart they are. Simpler explanation. Einstein thought there must be some hidden rule explaining this instant connection, like a secret code. But experiments, Bell's theorem, showed that there's no hidden rule. This instant connection is just how the world works at a quantum level. Quantum superposition and Schrödinger's cat. Imagine you have a magic coin that can be both heads and tails at the same time. It only decides whether it's heads or tails when you look at it. Simpler explanation. In quantum mechanics, particles can be in multiple states at once until you measure them. Einstein found this weird because in our everyday life, things don't behave this way. But experiments show that this is how tiny particles like electrons actually behave. Quantum decoherence. Think of a blurry picture that becomes clear as you bring it into focus. In the blurry picture, you can't tell what's in it, but as it interacts with your eyes or the environment, it sharpens into a clear, definite image. Simpler explanation. Decoherence is like bringing the blurry picture into focus. It explains why we don't see weird quantum behaviors in big things. Interactions with the environment make them behave in a clear, predictable way, like in classical physics. This idea helps bridge the gap Einstein wanted to understand better. Objective collapse theories. Imagine you have a special coin that, left alone, will flip itself after a while and settle on either heads or tails without anyone touching it. Simpler explanation. Some theories suggest particles can decide their state on their own over time, without needing to be measured. This idea aligns more with Einstein's belief that particles should have definite properties by themselves, not just when observed. Quantum information theory. Imagine you have a magic spell written on a piece of paper that can't be copied exactly. Any attempt to copy it results in a different, less powerful spell. Simpler explanation. In quantum mechanics, it's impossible to make an exact copy of an unknown quantum state. This principle is important for quantum communication, ensuring secure information transfer, which would interest Einstein because it shows unique quantum properties. Relational interpretation and contextuality. Imagine a chameleon that changes color depending on who is looking at it. For one person, it might appear green, and for another person, it might appear blue at the same time. Simpler explanation. In relational quantum mechanics, the properties of particles, like their state, depend on their relationship with the observer. This perspective helps address Einstein's concerns by suggesting that quantum properties aren't absolute, but depend on interactions. Quantum computing. Imagine a supercomputer that can try every possible combination to solve a puzzle simultaneously, thanks to magical powers, while a regular computer has to try each combination one by one. Simpler explanation. Quantum computers use principles of quantum mechanics like superposition and entanglement to solve problems much faster than regular computers. This practical success shows that the strange rules of quantum mechanics really do work, despite Einstein's initial doubts. At the heart of Einstein's unease with quantum mechanics lay a fundamental disparity in how reality was perceived. Classical physics presented a universe ruled by predictable laws, where the future could be precisely calculated. Quantum mechanics, however, introduced an element of chance, unsettling Einstein. He believed in an objective reality, existing independently of observation. Quantum mechanics suggested that observation played a role in defining reality, troubling Einstein. His unwavering belief in a deterministic universe led him to challenge prevailing interpretations of quantum phenomena. These challenges continue to shape scientific discourse, prompting researchers to seek a more complete understanding of the universe. Einstein envisioned the universe as an intricate but predictable clockwork mechanism, governed by fundamental laws. Every event, from galaxies to subatomic particles, unfolded according to these rules. To him, randomness reflected our incomplete understanding of underlying mechanisms. He believed that with complete knowledge, we could predict the universe's entire future. This deterministic perspective, while challenged by quantum mechanics, offered a vision of the universe as a grand, comprehensible machine. Despite mounting evidence to the contrary, Einstein found it difficult to relinquish this vision. To illustrate his deterministic view, Einstein often drew analogies to games of strategy and chance. Consider a game of chess, where each piece moves according to fixed rules. Given the initial positions and strategy, every move becomes predictable. Einstein believed the universe operated on similar principles of predictable rules. The complexity of the universe arose from the vast number of potential interactions, not inherent randomness. He saw the universe as a grand game, where a physicist could, in theory, predict its evolution. This analogy highlighted Einstein's belief in a hidden order beneath apparent chaos. Central to Einstein's worldview was the principle of locality, where objects are influenced only by their immediate surroundings. In physics, this implies that information cannot travel faster than the speed of light. This principle ensures events unfold in a causal sequence, preserving the fabric of space-time. Einstein staunchly defended locality, seeing it as fundamental to a rational universe. He believed any theory allowing for instantaneous action at a distance would undermine physics. This belief brought him into conflict with quantum entanglement, challenging his convictions about reality. To illustrate the conflict between quantum mechanics and locality, Einstein, Podolsky, and Rosen devised the EPR Paradox. They proposed that entangled particles remain intertwined regardless of distance. Measuring one particle's property instantly reveals the other's, seemingly violating locality. Einstein argued this highlighted a fundamental flaw in quantum mechanics, suggesting hidden variables predetermined the particle's properties. The EPR paradox ignited a debate that continues today, forcing physicists to confront the implications of entanglement. It challenged our understanding of reality and the nature of the universe. To grasp the EPR paradox, consider identical twins separated at birth. Despite growing up apart, they exhibit an uncanny connection. If one twin feels pain, the other might feel it too, seemingly telepathic. Einstein believed entangled particles might possess hidden, shared properties, like the twins' genetic predisposition. These hidden variables would eliminate the need for spooky action at a distance. Just as shared genetics explain the twins' connection, hidden variables could account for entangled particles' behavior. Einstein believed their fates were intertwined from the moment of interaction, predetermined by hidden factors. The EPR paradox challenged the classical notion of cause and effect, suggesting a holistic connection in the universe. Entanglement defied our intuitive understanding of space and time, troubling Einstein. He believed the universe should adhere to principles of logic and reason. The idea of particles influencing each other across vast distances seemed absurd to him. The EPR paradox forced physicists to confront whether the universe was as strange as quantum mechanics suggested, or if a deeper explanation awaited discovery. Driven by his conviction that the universe couldn't be inherently random, Einstein sought hidden variables. He believed uncovering these would reveal a deterministic picture of reality. This search fueled research into alternative interpretations of quantum mechanics. Hidden variable theories proposed that seemingly random outcomes were predetermined by factors we couldn't yet measure. Einstein's legacy lies in the spirit of inquiry and the belief that a deeper explanation of the cosmos is within our grasp. Einstein's discomfort with quantum mechanics stemmed from his belief in the universe's inherent orderliness. He found it hard to accept that the cosmos was governed by chance. To illustrate, imagine a surfer riding a wave, seemingly unpredictable but governed by hidden laws. Einstein believed the apparent randomness of quantum mechanics stemmed from our limited understanding. He reasoned that uncovering the hidden order would reveal deterministic laws governing particles. This belief fueled his search for alternative explanations, convinced that quantum mechanics was incomplete. Section 2. Piloting the Quantum World. A glimpse behind the curtain. One of the most compelling attempts to reconcile quantum mechanics with a deterministic framework is the de Broglie-Bohm theory, also known as the pilot wave theory. This theory, initially proposed by Louis de Broglie in 1927 and later expanded by David Bohm in the 1950s, provides an alternative interpretation of quantum phenomena that aligns more closely with Einstein's deterministic views of the universe. Imagine for a moment that each particle in the universe is not merely a point-like object, but rather a tiny boat navigating a vast, invisible ocean of pilot waves. This ocean, known as the pilot wave, guides the particles' movements, determining their trajectories with deterministic precision, in contrast to the probabilistic nature of standard quantum mechanics. Just as a current can steer a boat along a specific path, the pilot wave dictates the particle's every move, providing a hidden variable that restores determinism to quantum theory. In this interpretation, the apparent randomness of quantum mechanics arises not from inherent indeterminacy in the particle's behavior, but rather from our ignorance of the pilot wave's precise configuration and initial conditions. We can predict the statistical distribution of particle positions using the Born rule, much like we can forecast wave patterns on the ocean's surface. But the exact path of an individual particle remains hidden from view due to the complexity of the pilot wave dynamics. Pilot wave theory, while offering a deterministic explanation for quantum phenomena, introduces its own set of challenges, such as the non-locality required to maintain consistency with quantum entanglement. The nature of the pilot wave itself, for instance, remains a subject of intense debate among physicists. Is it a real, physical entity that propagates through space, or merely a mathematical construct that provides a convenient description of quantum behavior? Despite these open questions, pilot wave theory stands as a testament to the enduring allure of determinism and the ongoing quest to reconcile quantum mechanics with our classical intuitions about the universe, echoing Einstein's belief in an underlying order to reality. Section 3. Beyond the Horizon of Observation. A universe with hidden depths. Einstein's skepticism about quantum mechanics, while often portrayed as a scientific disagreement, stemmed from a profound philosophical conviction: the belief in an objective reality that exists independently of our observations. He found it deeply unsettling that the act of measurement, according to the Copenhagen interpretation of quantum mechanics, played a fundamental role in defining the state of a system. To illustrate his unease, imagine a vast, uncharted ocean teeming with marine life. A fisherman casts a net into the water, hoping to catch a glimpse of the creatures below. The net, however, can only capture a small fraction of the ocean's inhabitants, providing a limited and perhaps misleading view of the ecosystem's true diversity. Similarly, Einstein believed that our observations of the quantum world, while providing valuable insights, might not reveal the complete picture. Just as the fisherman's net only samples a small portion of the ocean, our measurements might only capture a limited aspect of a far richer and more complex reality. This belief in a hidden reality, one that extends beyond the reach of our current observations, fueled Einstein's conviction that quantum mechanics, while undoubtedly a powerful tool, was not the final word. He suspected that a deeper, more fundamental theory awaited discovery, one that would reveal the true nature of the quantum world and reconcile it with our classical intuitions about the universe. Section 1. Einstein's enduring question, a catalyst for discovery. Einstein's persistent questioning of quantum mechanics, far from being a footnote in the history of science, has had a profound and lasting impact on the field. His challenges, rooted in his deep intuition and unwavering belief in a deterministic universe, have spurred generations of physicists to refine, reinterpret, and ultimately seek to complete quantum theory. Imagine a master detective confronted with a baffling crime scene. The evidence points in seemingly contradictory directions, leaving the detective with more questions than answers. Rather than dismiss the inconsistencies, the detective embraces the mystery, driven by the conviction that a deeper truth awaits discovery. Einstein, in his relentless pursuit of a deeper understanding of quantum mechanics, played the role of this persistent detective. His challenges, like the detective's probing questions, highlighted the gaps in our knowledge and forced physicists to confront the profound implications of quantum theory. The very act of questioning, of refusing to accept the seemingly paradoxical aspects of quantum mechanics at face value, propelled the field forward. It forced physicists to develop more rigorous experimental tests, to refine their interpretations, and to explore alternative theoretical frameworks. In this sense, Einstein's skepticism, far from hindering the progress of quantum mechanics, served as a catalyst for its continued development. Section 2. Unifying the Cosmos. The Quest for a Theory of Everything. One of the most enduring legacies of Einstein's skepticism about quantum mechanics is the ongoing quest for a unified theory of physics. Einstein, in his later years, dedicated much of his energy to seeking a single, elegant framework that could encompass both the force of gravity, as described by his theory of general relativity, and the strange world of quantum mechanics. This search for a theory of everything, as it came to be known, was driven by the belief that the universe, at its most fundamental level, must be governed by a single set of consistent laws. Einstein found it deeply unsatisfying that two of the most successful theories in physics, general relativity and quantum mechanics, seemed to describe different aspects of reality, often contradicting each other. This quest for unification, while still ongoing, has yielded significant progress. Physicists have developed promising frameworks such as string theory and loop quantum gravity that attempt to bridge the gap between the macroscopic world of gravity and the microscopic realm of quantum mechanics. While these theories remain speculative, they offer tantalizing glimpses of a deeper, more unified understanding of the cosmos. Einstein's dream of a unified theory, a single set of equations that could describe all the forces and particles in the universe, continues to inspire physicists today. It's a testament to his enduring belief that the universe, despite its apparent complexity, is ultimately governed by a simple and elegant set of principles. Section 3. The Legacy of a Skeptic. Embracing the Unknown. Einstein's skepticism about quantum mechanics, while ultimately centered on his belief in determinism and an objective reality, also reflected a broader scientific mindset, a willingness to question even the most well-established theories in the face of contradictory evidence or unsettling implications. This willingness to embrace uncertainty, to acknowledge the limits of our current knowledge, is at the heart of scientific progress. Imagine a cartographer meticulously charting a vast and unexplored continent. With each expedition, new mountains are discovered, rivers are rerouted, and the map must be redrawn to reflect the evolving understanding of the terrain. The cartographer, rather than clinging to an outdated map, embraces the unknown, eager to refine and expand their knowledge. Einstein, in his persistent questioning of quantum mechanics, embodied this spirit of exploration and refinement. He recognized that our understanding of the universe is always evolving, and that even the most successful theories are subject to revision or replacement as new evidence emerges. His skepticism, far from being a sign of weakness, reflected a deep intellectual humility, a willingness to acknowledge that the universe often holds surprises that challenge our preconceived notions. Einstein's legacy in this regard extends far beyond the specific debates about quantum mechanics. It lies in his unwavering commitment to scientific inquiry, his willingness to question dogma, and his enduring belief that the universe, despite its mysteries, is ultimately comprehensible through the power of human reason. Section 1. Einstein's enduring challenge, the unfinished debate. Einstein's skepticism about quantum mechanics, though rooted in a profound belief in a deterministic universe, continues to resonate within the scientific community not as a refutation of quantum theory, but as a catalyst for deeper exploration. His persistent questioning, his demand for a more complete and intuitive understanding of the quantum world, serves as a reminder that our journey into the heart of reality is far from over. While the interpretation of quantum mechanics remains a subject of debate, Einstein's challenges have undoubtedly enriched the field. His insistence on locality, his unease with the role of the observer, and his pursuit of hidden variables have spurred decades of research, leading to more refined experiments, alternative theoretical frameworks, and a deeper appreciation for the profound philosophical questions raised by quantum theory. The search for a unified theory, a single framework that can encompass both the elegance of general relativity and the perplexing nature of quantum mechanics, stands as a testament to Einstein's enduring legacy. Whether such a theory will ultimately vindicate his belief in a deterministic universe or reveal even deeper mysteries remains to be seen. What is certain is that Einstein's quantum enigma will continue to inspire physicists for generations to come, driving us towards a more complete and profound understanding of the universe and our place within it.